So welcome back, everybody. And we hope you had a great weekend and that everything is going fine with the first midterm. So the topic today is actually to continue with where we started last week. And last week on Wednesday, we went through some numerical simulations of harmonic oscillations. And we added a damping factor. And then we asked ourselves, what do these types of damping actually mean? And we saw that we had cases which we call under damping, something which many of you have heard about as critical damping. And then we also had cases of something which we label as overcritical damping. So what we're going to do today, and also partly on Wednesday, is to make the mathematical derivations, which will link the mathematics with what we saw numerically. So numerically for us, it was actually just reusing the programs we had and just changing one single line and adding the acceleration. So now we're going to link this with the mathematics. And many of these things are based on rearrangements of cosine and sine functions, but it's useful to have seen these mathematical manipulations because these are things which you will see again and again in different physics courses. So this kind of link between what you see when you run a code and what you get when you do the paper and pencil exercises is actually quite important. And that allows us to, in a way, develop our intuition about the physical systems in many different ways. So let's try to dive back into the whiteboard. But before we do that, let me just quickly remind you of what we are planning to do this week. So we are going to look a little bit on driven oscillations also on Wednesday, parts of Wednesday. And then the second half of Wednesday, we are going to look at the solution of the midterm. And we are going to do the same thing on Friday as well. So that hopefully when Friday comes, you're basically set with what you need to do with the midterm. And then you can enter with peace on your heart into the spring break. Okay, so let me switch to the whiteboard here. And let us go through some of the mathematics which is needed and which many of you will meet again and again in different physics courses. So let's quickly remind ourselves about some of the things which we have seen. So what we have done is to solve a differential equation of this type here. And this is the standard harmonic oscillator equation. And then we divide it by the mass of the particle. And then we multiply this with x. So x is a function of time. And then we had minus omega 0 squared. And we introduced this omega 0, which is now defined as it's called an angular frequency, but you will also encounter this named as a natural frequency. Natural because it's defined by the constants of the system. So this is also pretty common when you do physics and when you scale your equations, or you divide away some constants, that you have some kind of a natural frequency or natural length scale which defines your system. So when we did exercise the Earth-Sun case in homework number 5, we plugged in a new length scales, which was defined in terms of an astronomical unit, which is a natural length scale for astronomical calculations. So let's also remind ourselves about the solution. So the solution is then something which is given in terms of t, and then we have an a, which is a constant, which are then defined by the initial conditions, and then we have a plus a b. This is the general solution, omega of t. Now, one of the things which we are going to do before we move on and go back to where we were on Wednesday, when we looked at the harmonic oscillations with a damping, is to remind ourselves of things which we did in homework number 1 about cosines and sines and exponential functions. So these are some useful mathematical relations which we are going to encounter again and again. And in particular, in harmonic oscillations, we know that since we have cosines and sine solutions, this means that we could actually try to rewrite our solution in terms of an exponential. So let me just give you these manipulations here. And we know that from homework number 1, the first exercise, we could rewrite this in terms of a plus minus I times a sine of omega 0 times t. So if we do that, you can see now that we can bring in this definition of the exponential in terms of cosines and sines, and actually rewrite the solution in terms of an exponential. So this is another way we can actually represent the solution. And if you now take a solution, suppose now you assume that the solution x of t is equal to some constant c of e to the I omega 0 of t. And if you plug this in to the equation for the second derivative, so this is your differential equation, what you get then is actually minus omega squared times c of e of omega 0 of t when I take the second derivative. And that's nothing but this omega 0 times this x of t. But now x of t was given by this solution here. So what we see now when we do this is that the exponential is also a solution to the same differential equation. So if you see a differential equation which has a second derivative and equal to a constant times a function x, then this should lead you to think that, hey, this can be a cosine sine. If it's a cosine sine, it can also be an exponential function. So I hope it's okay if I just give you the answer here of the second derivative. So it just gives you an omega, the first derivative, and then you have another omega, and then you have an I squared, and I squared is minus 1. Now what we could do then is that we could try and say that the general solution, x of t, is now given by a constant c of e to the I omega 0. And you will also see that the exponential with a negative argument is also something which satisfies the same solution. So we could actually have written this in a slightly more general form. So we have two constants which will be defined by the initial conditions. So in principle, you have an infinity of solutions. And when you specify the initial conditions, then you find the constants c and d. Now, one more manipulation which you can make, if you now look back at what we have here. So if you admire these lovely solutions here, so we have x in terms of cosines and sine. If we now simply introduce this term here, either with a negative and positive argument, and plug that one in here, we can then rewrite this equation in terms of cosines and sines. So what you would see then is that you could rewrite this as a c plus a d. Now I collect the cosine terms of a cosine omega 0 of t plus an I times a c minus d of sine of omega 0 of t. So the only thing I did now was simply to go back to the definition of an exponential in terms of cosines and sines, and I simply plug them in here. And then I kept the real part or the cosine part by itself. And then I have a constant c and d here, which now combine with an imaginary term to give the sine solution. So these are just a type of manipulations which you will see again and again when we deal with exponentials and sines and cosine functions and oscillations in physical systems. So if you're not too much used to it, get used to it, because this is something you will see again and again in physics. Then, if we now go back to the original solution which we had, which was given just in terms of cosines and sines, we have some a and b here. So what we will do now is simply to identify the constant a is now simply C plus D. And the constant B is simply I times C minus D. Now, there is an alternative here, which is often used in this type of oscillatory motion solutions. So a third alternative, so let's write that one down. Another alternative. That is to define a constant A. So this is a new constant A. So we have a new parameter A, which we define as a B1 squared. And I will show you what this B1 squared and B2 squared are. So these are just ways of rewriting the same equations. So if you now go back to good old Pythagoras, we know that we have an angle delta. We have a B1 here, we have a B2, and then we have an A here. So B1 is simply A times cosine delta, and B2 is simply A times sine delta. So I've just defined an angle, and this is something which is handy because it allows us to write the equation in a more compact form. And we can think of this delta as a phase shift. So we can actually kick off the system with a different phase. So we can now rewrite the solution. If we now go back to the solution which we had, so this x of t, and since we now introduce the b's, the new constants, so, and remember now that these are just constants, so we can name them whatever we want, plus b2 times sine of omega 0 t, and then I'm going to multiply and divide with a, so I can rewrite this as an a, and this is given by a b1 divided by a of cosine omega 0 times t, plus a b2 divided by a of a sine of omega 0 t. And then what you see now, if I now introduce these definitions, which I gave you here, in terms of a in cosine delta and sine delta, so I can put them back into the equation here. So I have a b1, which now has an a times a cosine delta, and b2, which is an a times sine delta. What I get then is a new expression, which goes like a times cosine omega 0 t times this cosine of delta plus a sine of omega 0 t and a sine of delta. And then we use these trigonometric relations of cosines and sines, and you've probably seen that one. So you would typically have a trigonometric relation which says that the cosine of omega 0 t minus delta is actually equal to what we have here. So if you go back to some of the standard trigonometric relations, if I take what I have in here, this is actually equal to this expression here. So that allows us also to write things in a more compact form. So we have, this is equal to a times a cosine of omega 0 times t minus some phase shift delta, which we haven't specified. Now, one reason why I bring this up now is that when we come to the case which we looked at last on Wednesday, when we put an external force and we put the force into harmonic oscillation, no, the system into harmonic oscillations, we are going to look at a solution which is actually given in terms of a mathematical form like this. Now, what you have here are just mathematical manipulations with cosines and deltas and cosines and sines and exponentials. But some of these manipulations allow us to write the equations in a more compact form. And sometimes this one with just a cosine is a little bit easier to deal with. Okay, so what we're going to do now is to go back to where we were on Wednesday, and we are going to look at the analytical solutions and how we can actually interpret. And as many of you said, for some of the motion, there would be a decay plus some oscillations. and at a certain point, the object would stop. Then we have what we call a critical damping, where the object just stopped almost immediately. And then we have something which is called overcritical damping. So these kind of things are things which you will see in all physical systems, which are governed by harmonic oscillations. And these are pretty many. So let's now go through the mathematics. It's perhaps not the most exciting thing we're going to do, but it's useful to have seen it. And the kind of approach which we often do then is actually to guess on a type of solution. And then when we have guessed upon this type of solution, we just see if this solution actually fits, like we did with a cosine and a sine. We find that by inserting that in the differential equation, that actually is a solution to the differential equation. And in this specific case, we know that this type of differential equation is something which gives us an oscillatory motion. So let's now look at the case with damping, but no external applied force. Eh? So let's try to do that and remind ourselves about the mathematics which we did. So when we added damping, we saw several things last Wednesday. And the typical form which we would add damping is to add to the differential equation something which goes like b times the velocity. And I'm going to stay in one dimension. If you go to 2 dimensions, you have to plug in a vector. And this is something which we would rewrite as b times a d of x of dt. So we are making an assumption now that this object is not moving too fast and that the friction term or the damping term is proportional with the velocity itself. This may not hold water if we go to systems which oscillate quickly. Then the damping term may actually have a different behavior. But let's make this assumption. Then what we ended up with was a differential equation which we solved numerically last week. So let me quickly remind you of that. So we have dt plus a b of d of x dt, and then we had plus k of x is equal to 0. So we have the acceleration, we have a velocity dependent term, and then we have a position dependent term. And as we also said on Wednesday, since we now have this dissipation due to the friction term or the resistance term, it means that energy for this system is not going to be conserved. So we are going to dissipate energy. So energy is transferred to the environment. So if we're looking at the total energy conservation, we would actually have to model the complicated interactions with the environment. And often we don't want to do that. Sometimes we have no idea on how to actually model the environment. What we did next was to divide by n. So we divided by n, and then we got rid of that one. So we had just the acceleration plus b divided by n. We had a dx dt. And then we remember that this k divided by n gave us this so-called natural frequency or angular frequency squared. Then the other thing we did was to define a dimensionless variable, tau, which is now given by an omega times t. So omega has inverse time as dimension times time. This becomes dimensionless. So this was a dimless variable, which we introduced last week. And then we could rewrite the equation if we also introduce a new constant, which is called gamma. And this constant gamma depends on the friction parameter. It depends on this natural frequency, and it has a factor of 2. This parameter, as you will see now, is going to play an important role, and it's called a damping coefficient. So how fast the system gets damped, coefficient. So how fast you can damp the system depends on the value of omega. And you will see this in the mathematics now. So this coefficient is actually pretty important in the analysis which is going to come now. And you will see that in the analytical solution, that the size of this parameter is going to govern how fast the motion comes to rest. So what we saw last time was the following. So we looked at a case where this gamma was smaller than 1. And in that particular case, when we did the numerical analysis and looked at the displacement as a function x of t, as a function of time, we would start at some initial value x0 time t0, and then we would see something like this. And the motion would come to rest. So this is normally called underdamping. And as many of you said last week, since it's going to oscillate a little bit, it means that the solution will most likely have some cosine sine component, but then it's being damped. So there has to be an exponential with a negative argument. And we are going to derive that now. The other case which we looked at was a gamma equal to 1, which is normally called a critical damping. Critical damping. In that specific case, what we saw was something like this. We had an x of t and time here, and it would simply just go something like this, quickly down to 0. So my drawing capabilities, as you probably have seen throughout the semester now, they are not the best ones. So please apologize me if this does not look like what we saw numerically. But we get a critical damping and the system goes quickly down to 0. The same thing happens when gamma is equal to 1, or is larger than 1. So this is normally called overdamping. So this is also a system where we damp quickly the solution, but we are going to have two terms which will compete with each other. And depending on the value of this gamma, we can get something which goes like this, or has a different behavior. So this is our x of t, and then we have this as a function of time. Another thing which we did on Wednesday last week was actually to look at the change of the equations where we added an external force. And we are going to find the analytical solutions of all these cases. So the thing which we did next, last week, was to look at the same type of equation, d of x dt plus k of x, but then we could apply an external force which has an amplitude, and then it has its own frequency of an omega of t. Now, this gave us a quite interesting situation then. Now, if we now look at the way we would scale this equation, so let's prepare the equation for an analytical study. So if we now look at the way we did it last time, one thing which we introduced when we introduced this variable tau, so we could actually with tau given by omega 0 times t, we could actually rewrite the equation in terms of this parameter tau. So we've got a d tau second derivative plus this 2 gamma of d of x of d tau. And I think I forgot something up here. Sorry, guys. I kept it like this. So let's bring back. And then we have a plus k. No, sorry, plus x, actually. And this is now equal, if we look at this force, when we now introduce these manipulations here, it means that this force, what we have now is an F0, but we have divided by the mass, and we have also divided by omega 0 squared. But then we have a cosine, and now we're going to introduce a dimensionless variable. So we actually have a frequency, and this is divided by omega 0 times tau. And what is common then is to rewrite this as a new frequency, which we call omega tilde. So what I'm doing now is actually to prepare the equations for the analytical studies. So what we get then, the final equation, which we're going to study, is a d of second derivative with respect to x. And we have this 2 gamma. And then we have the first derivative, which is the velocity. We have plus x. And this is now given by a new term. And I'm going to call this term here for f tilde. So I'm going to have an f tilde multiplied with cosine of this scaled frequency times this dimensionless time. So this is a type of equation which we now are going to look at and try to find the analytical solutions of. So we can actually find analytical solutions both to this equation and to the case where the force is equal to 0. Now, I just wanted to bring this up because now we have the complete package which we're going to study. And I just want to remind you quickly of what we saw when we run some calculations with the force as well. Because there's a lot of interesting behavior here. There's a lot of interesting physics, which is going to be dependent on the ratio between the frequency you apply and the frequency of the system. And you can get something which are called resonances, which we will study a little bit later. So what we did was actually to look at a system like this when f0 was different from 0. This is the final case, which we looked at on Wednesday. And we saw something like this. So we had this tau. We had our x of tau. We started at some x0. And then it went something like this. And then suddenly it was oscillating the same frequency forever. So what happens then is that the frequency omega governs the motion. And everything with the initial condition, which is dictated by the way the system looks like, is forgotten. So it doesn't even become legend, it is just forgotten, where you were in the very beginning. So that means when you look at the system, the way it behaves, so x0 is just forgotten, x0 is forgotten. Or rather, you could say that the system does not remember where it was in the beginning. So it sounds like me. Except that in my case, it takes a very short amount of time to actually forget where I was in the beginning. Anyway, so let's now look at the analytical solutions. This is what we analyzed numerically last week. So let's look at the case where f of 0 is equal to 0. So we put this external force to 0. Then the differential equation we want to solve is simply this one, plus 2 times gamma of dx d tau plus x equal to 0. So if you now think back to what we did without this term with the velocity, if you were to guess a solution here, what would you guess upon? What would be your guess for a kind of solution here? Because what we are going to do now is simply to plug the solution into the equation, and then we're going to see if it is a solution or not. And what are the constraints of finding a solution? So if you now take away the term with the dx d tau, if you wanted to guess upon a solution, what kind of wisdom have you gained till now about the type of motion? What would you guess upon? Yeah?
Sine or cosine.
Yeah, sine or cosine, or you could take an exponential, right? So an exponential would include both sine and cosine, right? So this is the kind of, we see from the simpler system that the motion has some sine, cosine, some oscillation type. But then we also see from the numerics that it has some kind of decaying behavior. And that could also be an exponential. So let's just guess on an exponential. And we are not going to say anything, whether there is a complex argument or whether there is a real argument. So let's just guess upon an exponential. And then we're going to plug it in. So this is what you see now is actually a pretty common trick when you solve differential equations in mathematics. So if you've taken a course on differential equations, you've probably seen something like this. So let's try to put it up. So we make a kind of ansatz or guess, and we simply say now that x of tau is equal to some constant, which we haven't specified. And then there is a parameter r, which we also haven't specified. And then it depends on time here. So this is not yet specified. So let's plug it into the equations, and let's see if we can do something meaningful and perhaps extract some wisdoms about the system here. So typically what I would do now is simply to plug in this in the equation. I plug this in the differential equation here. Plugging it into the differential equation means that the first term, so I get obviously the derivative, so I'm going to have this r of tau. Now, the term which you see here gives me obviously a second derivative, which gives us r squared. Then if I take the next term, this term here, I get a plus a 2 gamma. And then I have a new r. And the final term is just 1, it's just unchanged. And this is equal to 0. Now, clearly, if I put a equal to 0, I have a trivial solution. And we are not so much interested in that one, right? A equal to 0 is a solution, but it's not exactly what we are looking after, because when we solve things numerically, we saw that this object was actually oscillating. So we are going to assume now that a is obviously different from 0. And we're also going to assume that r times tau is different from 0. So the only way we can satisfy this equation then is to solve this second order equation. Plus 1 is equal to 0. And I guess you saw this, all of you must have seen this back in kindergarten, right? So you know how to solve this equation here. And we have two solutions. So these are the two roots. And let's see what happens here. So the solutions which we get are obviously an R1, which is minus gamma plus, and then I have a gamma squared minus 1. And then I have an R2 here, which is minus gamma, but minus gamma squared. So the solution which we are getting, x of tau, is going to be equal to a, and I just put in a constant a1, because I have two values of r, of tau, plus an a2 of e of r2 of tau. And now you see very clearly that if we now leave the square root, and if you just look at the term with gamma here, this is something which, when included here, is going to give us this kind of damping, which we saw in the first case when gamma was less than 1. So let's go back to this underdamping, which we saw last week. We have to be a little bit careful then. And let me try to see if you can see why this is something we have to be a little bit careful with. So let's go back to the underdamping. So when we did it numerically, we just fixed the value of this gamma to be less than 1. Now, if you now look at the solutions which you have here, what do we need to pay attention to in case gamma is less than 1? So we're assuming that gamma is a real number, okay? Because, yeah? Yes. So in this case, we get an imaginary root, and we have to be a little bit careful with that. So what we are going to do now is to rename this root here in terms of a gamma prime. And that's going to give us an imaginary number in front of gamma prime. So we're going to have an I times gamma prime. So I simply redub it, the root here, in as a y times gamma prime. So in this case, what we are doing is simply to rename gamma minus 1 as I times a gamma prime. And gamma prime is a real number. It's not a complex number. And the same happens with gamma, because we know that gamma was nothing but the friction constant, the mass of the object, and these are physical constants, so they have to be real numbers. So when we have this now, you see that we can rewrite the solution in terms of an A1. So our x of tau then becomes equal to an A1, and then I have an E of minus gamma, and then I have an E of plus I times gamma prime, plus an A2 of E minus gamma. Oops, I think it should be a gamma times, now I'm a little bit sloppy here now. So it should be gamma times tau. It's gamma times tau, and then an E of minus I times this gamma prime times tau. And we see now very clearly, when you look at the solutions, if you now pick this term, that is going to give us a damping piece, which we saw when we run the code. And the other term, the term which goes with the imaginary part, is something which will now give us the cosine and sine solutions. So we have been able to split mathematically the solution in terms of the two things which we actually saw when we run the code. So this actually agrees with what we've seen numerically. So it means that what we have, and let me single these terms out. Let's bring in some colors. So we have this term here. These are going to be the damping terms. And you see now that the damping is governed by gamma. And that's why we call gamma a damping constant, because the size of gamma tells us how quickly this will die out. So if gamma is a small number, this is going to oscillate quite some time. If gamma is a large number, it's still less than 1. This may actually be damped pretty fast. And the next, which we have, this term here, if we take this one, this is going to give us the cosine and sine oscillations. So that's pretty neat. That agrees with what we saw numerically. So now that we've gotten quite ambitious and we see that we can actually solve the problem, we could now say, hey, what happens when gamma is equal to 1? By the way, we can always rewrite these equations here in terms of cosines and sines if you want to. So if you can rewrite the solutions here in terms of an A1 plus an A2. If you take this constants of an E of minus gamma of tau, and this is multiplied with a cosine of this gamma prime of tau, plus an I of an A1. So this is the same manipulation which we did in the beginning of the lecture, of E of minus gamma of tau over sine of gamma of tau. And then we can obviously relabel these coefficients. If you don't want to have A1s and A2s and you prefer B's, you can actually call A1 plus A2 for a new constant B1. And then you can call I times A1 minus A2 for a new constant B2. So these are just variables, constants, right, which you can define. And these constants are defined by your initial conditions, always. And we have an infinity of solutions because we have an infinity of initial conditions, right? So this is the general solution of the equation. So what we could do now is go to the case where gamma is equal to 1, because that's a little bit simpler. And if we do that, we would get the following. So the next case is normally what we call critical damping, gamma equal to 1. So this is called a critical damping. So in that specific case, that means that gamma is equal to 1. This is just equal to 0. And then we can read off the solution immediately, but there's something strange here. So if we now look at the solution, if we now go back to what we had an A1 of E to the minus gamma of tau plus an A2 of E minus gamma of tau. That doesn't look right, right? So one thing you should keep in mind, if you have a second order differential equation, the solution is normally composed of two terms. If you have a first derivative, there's normally one function. If you have a second derivative, because then you get more initial conditions, you have the velocity and you have the position, then you normally get two solutions. And we've seen that with the cosines and sines. So this is a kind of thing just to remember, unless you know this from differential equation solutions. If you have a second derivative, there are normally two solutions, or it's a linear combination of two solutions. If you look at the solution here now, there's something strange, isn't it? What strikes you as strange here? Yeah?
There wouldn't be any oscillation because...
So in this case, you don't have any oscillation, but if you look at the mathematical form, so that's a very important point. There is no oscillation because gamma is a real constant. So this just dies off immediately. But if you look at the two terms here, what would you say, except for the constants A1 and A2? What is their mathematical form? Are they the same or are they different? They are the same. So that means that irrespective of constant here, we could actually have written the solution as A1 plus A2 times the same mathematical function. So what you can show, and this is also in the notes, so I'm just going to set up the solution here, is actually you need a new solution because you have a differential equation which has a second derivative. So you can actually show, and you can also see the derivations in Taylor. So I just wanted to, what you can show now is that you need a solution which goes like x of tau, which is equal to an A1 of E minus gamma of tau, plus a new solution which goes like an A2 of tau of E minus gamma of tau. So if you insert this solution which you see here in the differential equation, if you do that, so just try that, to plug that one in the differential equation. In order to solve the differential equation, so I'm just giving you a hint in the way you can prove that this is a solution. So in order to prove that this new thing here is a solution, you plug it into the differential equation, and then you will see that the only way you can find a solution is that gamma is equal to 1, which we started with. So that means that this is consistent with the differential equation and gamma being equal to 1. So the only thing you need to do is actually calculate the second derivative and the first derivative. And then you will get an equation which is fulfilled only if gamma is equal to 1, which we started with. So the circle is fulfilled then. So that's the typical way you would show that this is a solution. And now you see very clearly that you have the damping term, and there's obviously going to be a competition between them, which will depend on the size of gamma and how long you simulate. But as it was said here, what you have now is a damping factor. There is no oscillation. There is only a damping factor, and that's what we saw numerically. So this is normally called the critical damping because then the oscillation disappears. So in this case, we have a damping, which depends obviously on the value of gamma. And in our case, gamma is equal to 1. In this specific case, we put it equal to 1. So gamma is well defined here. And remember now that this variable gamma was defined as this parameter b divided by the mass times omega 0 times 2. So these parameters, and now we're simply putting them equal to 1 in this specific case. So clearly the way the system gets damped depends on the ratio between friction or resistance, the mass of the system, and then in our case, this natural frequency of the system. And this is quite interesting because that tells us a little bit about the size of the damping. And you can tune the system if you know the values of B. You can obviously tune the natural frequency so that you actually can get critical damping, under damping, or over damping. But what we have now is clearly an example of a damping term here and here. So that gives us damping. And it's the exponential term which actually kills the motion here. Then it depends obviously on the initial conditions. They will define the parameters A1 and A2. The next case, which we're going to look at, is the case of the strong damping. So that's the final case. Strong damping. And let's look at the mathematics here. In this case, the mathematics are a little bit more straightforward. So we would have a gamma, which is larger than 1. So that means that gamma squared minus 1 is always real. So there's never a problem with looking at that term. And the solution when we plug it in is now given by two terms which will compete with each other. There's an A1 of an E minus, and then we have a gamma minus a gamma squared minus 1 times this dimensionless time. So this is an A1 plus a new parameter A2, which is again defined by the initial conditions of a gamma plus a gamma squared minus 1 times tau. And what you see here now is that we have two damping terms. And the way this is being damped will depend on the value of gamma. So we have damping only. And how fast it gets dampened depends on the size of gamma. So in our case, we could now take a look at a situation where gamma is much, much larger than 1. So let's suppose that. If that is the case, then gamma squared minus 1 is normally close to gamma. We can neglect 1. That means again that when we look at the solution, we are going to get an x of tau, which is approximately equal to A1. And then we have 0 argument in the first one, plus an A2 of E to the minus 2 gamma of tau. And then depending on the initial conditions and the values of A1 and A2, this is now the damping is going to be driven by this term with E to the minus 2 gamma times tau. And now we have assumed that gamma is very large. So if you have a large initial condition, A1, then this term here may have to work a little bit before the motion comes to rest. If A1 is very small, this dies out immediately. So these are the kind of games we can now play, but you see clearly from the mathematics here how this relates to what we saw numerically. So the kind of intuition which we built up running a numerical calculation and visualizing the results is something which we see back in the mathematics here. And that is in a way, is a little bit assuring, isn't it? And this is also a system where we can actually solve things analytically, and we can compare that directly to what our code spits out. So on Wednesday, we're going to steal some of your time on looking at the forced oscillation and how we can get the analytical solution with a forced oscillation as well. And then we have a complete picture of damped motion and damped motion with a forced oscillation. And many of these physical systems are actually systems which you can realize in the lab without too many problems. And they're pretty close to what you might see in reality. And if you go to electronics, these type of equations, actually the type of equations you end up solving, if you replace these parameters with the charge, the electrical current, and the resistance. And then you can solve the same type of equations, and you can study the motion by looking at, for instance, what we normally call a RLC circuit, where you have an inductance, a resistance, and a capacitor. And they really match almost perfectly what you run theoretically and numerically. Okay, so feel free, ask questions, hang around if you want to. And yeah. If not, we just see each other on Wednesday. Oh.